10월 초에 가서 한 열흘 정도 있을 계획인데
예.
스노플레이크 이 퍼포먼스가 좋아지고 있어. 음, 주가가 올라가는 모양이야. 음,
레비뉴가 1 빌리언 퍼 쿼터를 이번 쿼터에 처음으로 쳐서
음.
반응이 괜찮은 것 같습니다. 예.
뭐 그런 인용식 기분이 좋아지겠네. 주가가 오르니까. 음,
예.
음. 우리가 시간이 됐는데 이제 시작을 하면 될 것 같아. Now let's get started. Welcome to Data Science Seminar. Today we have a unusual speaker. First time my former student who worked with me on uh, in the database systems from the beginning, developing P-time and joining the startup that I created in Silicon Valley, and then went through SAP to develop SAP HANA distributed in-memory database systems. And then he moved to, I encouraged him to leave SAP and to start new things. And then he moved to Amazon in Seattle. And then he was recruited by Snowflake before Snowflake went to IPO. So go ahead, Yongshik.
Yeah, thank you for the introduction, Professor Char. Let me start sharing my screen first. Yeah, I'm Yong-Sik Yoon from Snowflake database engineering team. So today I'm going to talk about my kind of the journey through P-time, SAP, Amazon, and Snowflake, and together with the evolving data landscape, with my personal kind of the experience. So journey through the modern database systems, cloud, and the nowadays AI data cloud with Snowflake, I will touch a little bit upon. So the little bit of the agenda to begin with, like I want to talk about a little bit of how database system evolved over time, and also along the line with it, my career journey through, and also the lessons learned from HANA and AWS Aura database and beyond, and a little bit of the summary of the Snowflake architecture and uh, development principles and a little bit of deep dive on a couple of things we do at Snowflake. And Snowflake has a modern AI data cloud use cases and examples. And if time allows, I'd like to have short demo if possible, and closing with the Q&A. Okay, so very starting with a very simple like a statement here, like a database evolution. So database systems, uh, yeah, have evolved significantly over time. And very early days, system focused on the basic kind of the data storage and retrieval, like file system. And modern systems offer more advanced analytics and scalability. And then when it comes to the cloud technologies, I mean, it has been revolutionized database management, which I experienced together with Amazon AWS Aurora databases. And now it is going to be more and more important, and scalability is super important, and also the AI integration also very important. So AI integration enables intelligent data processing and insight, like how we want to serve the AI from data serving layer, data platform perspective. At the same time, how we can leverage AI to power the database technology. There's two different angles. So a little bit about me. So as you can see here, I have the one nice picture here. In the background, this is the uh, Switzerland Alps. So here, in the middle, the Professor Char is here, and on the very left-hand side, this is me. And all these people has been working on the database development. This picture took August 2005, so 20 years ago. And I think almost everyone here is still working on the database development. I mean, the database industry here and there, SAP, Amazon, the Snowflake, and so on. So I'm working at Snowflake, and these two are working at SAP now, and Zhu Chang is the head of the labs, SAP Labs Korea, and Sung is working at AWS. I hired him when I was there in the AWS Aurora databases, and now he's moved to the EMR Spark front of the Athena, AWS Athena, and there are people still working on SAP HANA in-memory database, and these last two, they are working in my team like a senior engineer and principal engineer query processing platform team at Snowflake, and I hired them when I was in Amazon, so they relocated to the United States here in Seattle area, and also one down there in Bay Area. And after I joined Snowflake, they joined Snowflake a couple of months later. So I dedicated the entire my career, like 20 plus years of my career, to database engine development here and there, and focusing on mainly the real world performance issues with the query optimizer. I think the query optimizer is the brain of the database system. And I have opportunity the switching between a different role as an individual contributor, like a database software engineer, the tech lead, and managerial role back and forth. Like I was the tech lead and software engineer at back in SAP, and became a engineering manager. And also, when I joined the Amazon Aurora database, I was the first one, I mean, to joining the database development team, working on the query processing layer, and then build a team around the query processing afterwards and became the manager. And Snowflake, the same. I joined as a engineer to develop the query processing capability around the materialized view, and I was able to build the team around the compiler. Sorry, there was any question? Okay.
It was the noise.
Yeah. So this is my career journey. So I have multiple international relocation and switching roles, and it all starts with this TIM systems. P-Time in-memory database. I was the graduate student and researcher at TIM system, and there I was able to get an opportunity to implement very first version of the query optimizer. And then it got acquired by SAP, and it was the inception of the SAP Labs Korea. And TIM acquired by SAP, and back then I was the software engineer and tech lead manager of the query processing team. And eventually, 2010, the SAP HANA was announced as was one of the founding members of SAP HANA. And 2014, I decided to relocate to the Germany, the Waldorf SAP headquarters. So there I was playing a role as an individual, like a database architect in query processing layer, and I was get an opportunity to more closely working with customers and enterprise applications, and also have an opportunity to work with the next version of HANA internally. And then I got a reach out from Amazon web service database team, Aurora MySQL team, and they're like it has been very successful. I mean, the Aurora MySQL and the Professor Jung Hyung-soo was the founding member of the Aurora MySQL, the uh, cloud scale distributed storage was the one he founded. He was one of the founding member there, and it has been very successful. And when it gets successful, everything is about the query performance. So it was like they made an innovation in the file system layer logging and distributed storage. But eventually they need to improve the query performance, and it was the MySQL kind of the clone, but it was not very satisfactory from the serious enterprise customer perspective. So that's why they wanted to have someone like me to improve the query performance. So what I did there was to improve the query processing layer with the parallel query processing and introducing the hash join and making the like storage layer smarter, because storage layer was distributed file system and it was very intentional to decouple the compute and storage, and that was the main innovation they did. But there are a lot of kind of the resources available in the storage layer as well. So making storage layer more smarter is something I did, like for example, the pushing down the projection, pushing down filter or aggregation so that it can pre-aggregated, pre-filtered and uh, projected at the storage layer to minimize the data IO network data transfers. And as I mentioned earlier, I was the first software engineer in Seattle area working on query processing team, and eventually ended up created multi-location query processing team between Seattle and Palo Alto, San Mateo, Palo Alto, the Bay Area. And then 2019, Aurora is kind of the OLTP focused transactional databases. And when there is a transactional databases, there is a OLAP, the analytical databases. And in AWS ecosystem, Aurora was the OLTP and Redshift was the OLAP databases. And there are customers using both Aurora and Redshift for OLTP and OLAP. And then I started seeing Snowflake as a competitive landscape. Like customers are leveraging Aurora as a OLTP front end, and then eventually move the data to the Snowflake instead of Redshift. The Redshift was I would say the first generation cloud kind of the database system, but Snowflake is the really the cloud native kind of the database analytics system from ground up. So I got reached out from the VC and the founders at Snowflake, and who are from Oracle and also who are very kind of the expert in the query processing and optimizer layer. And I got like kind of intrigued by their mission and vision. So I joined there before the IPO. So I was also the main office was down there in the Bay Area, but I was the first member on SQL team. Within the Snowflake, we call it query processing team, the SQL team back then, just one SQL team without any additional like area specific teams. And eventually now I'm the director of engineering at the SQL team, responsible for this query platform, which is like I created a team specifically for compiler and optimizer space. So it is also the multi-location team, like here in Seattle Bay area and down there in the Bay Area, there are half and half of the engineering teams working on the compiler optimizer query platform space. And that's my journey so far. So I moved from Korea to Germany and now eventually United States. So along the line, there has been the shifting the data landscape. So why do we need the modern databases? So that is something I want to touch upon a little bit. So the volume, so petabyte to exabyte scale, and also the data type is primitive data type used to be the case in the old days, but nowadays everything is data. So both structured, semi-structured, and unstructured, everything is stored in the database systems. And also velocity is really important. So people want to have the near real-time or real-time data processing and analysis. And hardware advanced a lot, like chip storage, like S3 and Amazon, for example, object storage, very cheap, and fast network and powerful CPUs and GPUs, and memory is affordable. So that's why we have the HANA in-memory databases in the enterprise world as well. And the third pillar is a software paradigm shift, like distributed systems for scale out and microservice architecture and open source like Postgres, MySQL, and Iceberg is another open data lake kind of the systems. And yeah, rapid innovation comes from open sources space as well, including the Spark, Hadoop and Spark as well. So the why modern databases thrives and why there are many kind of the new startups serving as the platform serving layer as a databases. So those modern databases enables like faster data processing for near real-time or real-time insight and analysis, and also offers high scalability and reliability and the large data volumes, and also provides advanced analytics, including the AI integration, like easy to use standpoint, and also reduce the cost, like pay as you go kind of the model for the cloud vendors. So these are the kind of the characteristics of the modern database systems, and why the customers are moving over to the database, modern database systems. And main goal is to like they don't necessarily need to have the DBA on their own. Like everything will be handled by cloud database providers, and what they will focus on is their own kind of a context application. All the query performance and the database access performance will be on us as a database platform providers. So all the companies, customers on top of these modern databases should be able to just focus on what they are interested in, which is the application logic and application layer, instead of the struggling with optimizing the single query performance here and there using controlling knobs in the databases and tuning and the hint for query processing and so on. Okay, so the starting with the SAP HANA in-memory powerhouse, I would say. So I was as I mentioned earlier, fortunately, one of the founding member of SAP HANA. So what was the key innovation in SAP HANA? So it was the first successful in-memory computing, the processing data directly in RAM, bypassing the disk I/O bottlenecks. And also the columnar storage is optimized for analytical queries. It comes with a compression benefit. And also the OLAP and OLTP convergence, it can run transactional and analytical workload on a single system. And what lesson learned from SAP HANA was the like power of the data locality through this in-memory, the keeping data in memory, which dramatically boosts the performance. And optimizing for this very detailed level kind of the optimization, code level optimization, like memory access, cache consciousness, and also the new indexing and the query processing technique. Those are very critical for mission critical workload. And there's also the challenges in the convergence between the OLAP and OLTP systems, and HANA was able to provide both columnar storage and the row storage for LTP purpose as well. But there was the scalability limit. So while the fast and scaling the in-memory systems, like the in-memory systems beyond a certain point becomes very expensive and complex, and you need to add more and more memory. And this was before the cloud era. And then to the Amazon Aurora database, AWS Aurora databases, and my role there was as an engineer and also the leadership at the Amazon Aurora MySQL flavor, to be more specific. So key innovation there was like cloud native design. As I mentioned earlier, like it built specifically for the cloud, to leveraging the AWS infrastructure. So yeah, as I marked here, the log structured distributed storage systems and compute and storage separation, those are the major key innovation in AWS Aurora databases. So it decoupled compute and storage, separating the database engine from its underlying the storage, and the log-based storage, distributed and fault-tolerant self-healing storage system. So this is not just local SSD storage, but it is more of the block storage, having the 3 copy for 3 availability zone. And it also offers the drop-in compatibility with MySQL, and later on it added a Postgres SQL flavor as well. And simple pay-as-you-go pricing, and whenever you use it, you pay for it, and you can, if you don't use it, it will automatically pause or shut down the instance, and delivered as a managed service. So you don't necessarily need to take care of all the kind of the toiling there. So lesson learned here is the benefit of the cloud elasticity. So scaling the compute and storage independently is very kind of the transformative, and it was designed for failure. So embrace the distributed system principle for resilience, and global scaling. So reaching the millions of customers worldwide, which requires the robust infrastructure, which Amazon is pretty good at, providing the different micro services at different level, from S3 object storage to EBS block storage, and more complicated database application on the top. And also operational excellence, like automating the database management in the cloud offers a lot of benefit for customers. So that's the main reason why the Aura was the fast growing kind of the product in AWS history. And then eventually on the Snowflake. So now I'm with the Snowflake. So actually this was my second startup, as Professor Cha mentioned earlier. So TIM system, P-Time, was my first startup, university startup, successfully acquired by SAP. And Snowflake was my second startup, successfully did the IPO. And Snowflake is my fifth database engine I'm part of. So I have been working on database engine development here and there, and many different places, and also the different area in the system, from metadata, query processing, DML, DDL, and the query, the read statement, and plan caching, and so on. So all different areas. And now I'm focusing more on the uh, as I mentioned earlier, the brain of the databases, which is the compiler optimizer space. So yeah, So based on my experience along the line with this the changes in the industry and the landscape in the database, so what what I learned was like scalability, elasticity is super critical. Fixed size systems are no longer sufficient. And also we need to break down the silos for analytics and transactions. So unified data platform are very essential. And optimizing resource consumption is the key because customers are also very much aware of the concern about the cost performance as well. And also the empowering the many different kind of the users, diverse users is also very important. Empowering the analyst who doesn't have enough understanding of the technical aspect of the data management, and also the data scientists, they are mainly working on the Python and the notebooks, and the developers, have more understanding, traditional understanding, the working on the database, writing the SQL and queries and so on. And the future is the cloud native and data centric. So building system that fully leverages cloud capabilities will be successful. And leading to the next generations, I mean, this is also required like Tenet for truly modern data platform. And this is something actually we are working on at Snowflake. So let me dive a little bit deep into the Snowflake here. So what is the Snowflake? So Snowflake not just a data warehouse, but the data cloud. And nowadays it is more of the AI data cloud. And it offers global network where thousands of the organizations mobilize the data, and single integrated platform for all your data, like structured, semi-structured, unstructured. And also it runs on top of the major cloud vendors, AWS, Azure, and GCP. And core idea here is that eliminating the data silos and complexity and provide secure, governed access to live the shared data, and enables diverse workload, data warehousing, data lakes, data engineering, AI, ML applications. So Snowflake want to be a one-stop shop for everything around the data. And what I meant by the global network is that because Snowflake also offers like the decoupled storage and the computing layer, it enables very easy to share the data, and copy and clone is also very cheap. So providing the very secure data governance, but you are able to easily, share the data across the board with the proper authorization and authentication. So briefly put, this is the traditional architecture of the data warehouse. So there is a lot of the front end kind of the application like OLTP databases, as I mentioned earlier, systems like Aurora, and then there will be the ETL, and there the enterprise data warehouse, and there is many different consumer of the enterprise warehouse, and also data lake and Hadoop is interact with the very well like formula cleansed, the enterprise data warehouse as well. Like this has been the traditional architecture in the past, but what Snowflake is targeting is as I mentioned earlier, one-stop shop for everything on data. So everything will stay within the Snowflake, and Snowflake will offer all different aspects of the data access, data application, and data processing. So let me quickly go through the key design principles Snowflake. So first, simplicity and easy of use. So fully managed service with a very minimal administration. So standard SQL interface, of course, and focused on the user experience and also the zero tuning and zero knob kind of the development philosophy we are following through. And that has a lot of challenges for us to deliver, because without exposing the controlling knobs for users and also the query hint to force certain join order for customer to control, it is very difficult for us to satisfy each and every kind of the workload and queries. But that is something we have to deal with for customers, so that they can simply use the Snowflake and run the query, and they don't necessarily need to care about performance at all. So that brings me to the next kind of the principle, which is performance and efficiency. So we offer Snowflake as the columnar storage, micro partitions, and together with the intelligent caching, and also the advanced query optimizer with also the vectorization, of course, during the execution as well. And it optimized for large scale analytics workload. And then elastic scalability and concurrency. So independent scaling of compute is the key. The virtual warehouse is the what we use. So you can spin up the warehouse whenever you need. And workload isolation ensures, this kind of the workload isolation ensures the consistent performance for mission critical application. And it handles thousands of concurrent users and queries. And at the same time, cost efficiency. So we separate the billing for storage and compute, and only pay as you go, like a pay per second compute billing, and automatic suspension and resume of the warehouse we support. So customer doesn't necessarily need to take care of this administrative work to reduce the cost. We do it for them. And robust security and governance. This is also super important. So end-to-end encryption and the granular role-based access control, data masking, tokenization, row column access policies we provide. So this is another different picture of the Snowflake as a one platform for many different workload, not just as a data warehouse, but as a data cloud for every different aspect of it. Yeah, I don't want to repeat the same thing again, but just wanted show some aspect of it here. So data exchange is something I may want to highlight here. So you can share very easily like your data with external kind of the consumers with data governance. So you can selectively share the certain columns, for example, or certain rows by defining the like row access policy for that specific data. And you can also define the secure view so that the consumer will see the data you defined, and also provide a masking policy so that some sensitive data will be masked out when consumer access the data. At the same time, consumer is not going to be able to see what's inside the view, so view definition is not going to be visible to those consumers, together with the data security and governance as well. So this is the Snowflake, the architecture in a very abstract kind of the fashion. So there's a kind of the centralized storage layer, and it interacts with the cloud object storage, stores all data in the object storage. So Amazon S3, AWS S3, Azure Blob Storage, and GCP as well. And we store data broken. We broke data into the immutable compressed columnar micropartitions, and that is the unit of the data access. And yeah, columnar compressed, encrypted, and self-describing. So it has each micropartition has its own metadata and header. And as I touched upon earlier, because of the decoupling of the data and compute, it enables easier like zero copy cloning and time travel and data sharing. And also multi-cluster compute layer, we call it the virtual warehouses, independent compute clusters, separate compute resources for different workload. You can create as many as possible, as many as you want. So it offers elasticity, scale up and down, and suspend the rhythm automatically, and no resource contention because you can spin up the independent, isolated um, virtual warehouses, and also pay per second, like only pay for compute when it's running. And there's a cloud service layer we provide. This is the global service layer, we internally call it, the centralized brain of the Snowflake. So compiler optimizer sitting in this layer. So this layer, global service layer, we have the metadata management of all tables, columns, micro-partitions, metadata, and this micro-partitions has kind of the zone map, like for each column, the min max value and number of distinct values and number of null count to optimize the performance and also the input for the query optimizer. And we have very sophisticated query optimizer leveraging those kind of the statistics, which is always up to date. This kind of the zone map, the metadata, micro-partition level metadata. And rule-based access control and data encryption, security and access control is there. And transaction management offering ACID properties across distributed compute. And workload management, lastly, the routing and queuing the query. And this global service layer is kind of the multi-tenant layer, and this storage layer is per account per customer, and warehouse is also the per customer, but global service layer is the multi-tenant. So going into the Snowflake's development philosophy. So user-centric design. So we want to build for diverse need of the data engineering, data analytics, data scientists, database engineers, and also application developers. And to serve all different kind of the need, our main basic philosophy is the no knobs, no controlling tuning knobs. So focus on removing all the friction and complexity from the data workload. So everything we are gonna do is the under the hood. We are gonna optimize your workload for you, and every kind of the regression or the performance improvement will happen under the hood. And we are doing the continuous innovation, which takes a lot of effort, like rapid release cycles. Actually, we are doing the releases on a weekly basis, and every enterprise customer, very large kind of the financial mission critical kind of customers, they need to upgrade their data version each and every week. So every week we release a new version and they have to update to the new version. We don't offer the different flavor or different version of the system, only single version and the previous version for retry mechanism. So every customer need to move over to the new version. And it also comes with a benefit, like delivering the new features and improvement in a constant fashion, and very responsive to the evolving market need, like unstructured data and LLMs. So new features will be delivered very quickly, very rapidly. And also performance optimization at the core, we are very obsessive in terms of my team, like a database engine team, core engine team. They are very focused on obsessive focus on the query optimization and execution efficiency. And like from customer standpoint, this is very good, but the company standpoint, probably it is not always the good kind of the case, because if we improve the performance, as you can imagine, like if the workload, customer workload stays the same, we will see the decreasing revenue if we improve the performance. So there is a little bit of the like the mm, some back and forth kind of the discussion how we want to deliver the performance optimization. At the same time, we can leverage, I mean, we can encourage customers to learn more queries so that they can use Snowflake more and more, so that we can eventually see the revenue growth. I mean, a lot more jobs are running as Snowflake compared to the last month, last quarter, last year. So we are keep improving the performance under the hood, and it constantly delivering those kind of the performance optimization and new features on a weekly basis. And also semi-structured data. So there's JSON, XML, Avro Parquet, or I mean, this is more of the JSON, XML is more of the like data layout, and the Avro Parquet or C is more of the storage kind of the layout. So we store the both structured and semi-structured data, and in a table columnized format. And for JSON and all the XML or the variant data type, we also kind of the flatten and columnize it, and also in a workload awareness way. And SQL syntax also is a very simple, like a dot dot notation for JSON access, and store the original document as is, like JSON and or XML, or like we also support structured data type for Iceberg and the traditional Snowflake proprietary table format as well. So you don't necessarily need to clean and denormalize the data. You can just ingest data as it is, and metadata will be automatically collected and data will be columnized automatically. And coming into the little bit of the technical details here, I want to touch a little bit about the micro partition. So we store the data in a file, the micro partitions, and micro partitions are very small file that store data in columnar format. And we also store the metadata for each and every the micro partition. And yeah, we can also leverage this micro partition metadata for better performance, which is pruning. So pruning is kind of the pretty like much self-explanatory. So pruning is just to remove anything like unnecessary before, I mean, the processing the query. So how we avoid like scanning entire table, entire partition that are known to not qualify an operation. So as you can see here, so these are all the partitions, and for example, like if you like if this is the raw kind of the click stream from IoT example, and there's also the data date time timestamp, then it will automatically cluster by the timestamp. And if a query was filtering by event date or event timestamp, and we should be able to prune out the most of the unnecessary micro partitions and only scan the necessary ones from the storage, because we maintain the metadata of the min-max value of the certain column. We maintain that, so we can leverage that kind of the metadata. And this is very simple example to explain the gist of the pruning, but the Snowflake have very sophisticated logic to prune for very complex predicate. And Query Optimizer can prune out the data during query compilation, but also Snowflake can prune the data during runtime through the Bloom filter, join filter. This means the Snowflake will propagate filtering through the join as much as possible, and we will prune out the data not only from during the compilation through the metadata, also during runtime we will leverage that. So effective pruning is the key in the optimization and performance in Snowflake. So this is the more explanatory example of the clustering. So to best to get the best benefit from the pruning, as I mentioned in the previous slide, the clustering is super critical. So this is the one of those examples. So let's say you have a table that has a natural ordering key column of the date, and Snowflake automatically tries to put all the record of the same date in the same micro partition, and this will reduce the amount of the micro partition to scan when you query the particular date. But if you have the ID as a additional kind of the predicate condition, then you still need to touch the these three partition in this example, because natural ordering is by date, but there is no kind of the clustering based on this ID. So you have to scan these three micro partitions in this specific example. So, but if you add the explicit clustering, which is date and date and ID, then it will very well cluster like this. And for this specific query, this query can be answered just by scanning one single partition instead of three. So Snowflake offers, the user should be able to define the clustering key, and the Snowflake offers automatic clustering, and it seamlessly and continually managed all the reclustering as needed of the clustered table. So after the clustered table, the clustering key has been defined, reclustering does not necessarily start immediately. So Snowflake only recluster the cluster table if it will benefit from the operation. So with automatic clustering, Snowflake internally manage the state of the clustered table as well as the available resource, the nodes, serves, memories, and so on. And this will be used for automatic clustering operation in the background. And this allows Snowflake to dynamically allocate the resource as needed, and resulting in the most efficient and effective reclustering. And also it try not to perform any unnecessary reclustering. So only when the table would benefit from the operation, it will trigger the clustering as a background job. So that was the little bit of the technical deep dive on the one very single and simple example of the query optimization, how we optimize the query performance, leveraging the available metadata and clustering, and also the automatic performance aspect of it. And next I want to talk a little bit about the development priority at Snowflake. How do we decide in terms of what items we want to work on? Do we want to work on improving the benchmark numbers such as TPCH, TPCDS? That is not the case at Snowflake. So we have as Snowflake is the native cloud databases, we have all the data available on the cloud. In terms of the telemetry, so we can do the data. We can have the data-driven approach when it comes to what would be the next thing we want to work on. So here, what is the data-driven development and how we do it. So all the features. We have the usage tracking available, so we should be able to get some insight through the real world production data. And also, as I mentioned earlier, we have the very rapid release cycle, so weekly deployment to all environment to enable fast feedback for all engineers at Snowflake. And service-oriented architecture, of course, runs as a service with the real-time system-wide metric. And centralized data, so all valuable system information will be ingested and to the centralized database, another internal kind of the Snowflake data warehouse. We call it the Snow House. So here, as you can see, from idea, we want to evaluate the status quo, and we want to propose the new design, how we want to improve that specific kind of the workload, and implement and roll out, and we evaluate how successful our new improvement or the new feature, and then refine the design and so on. So these blue boxes in blues are the where we are kind of the able to utilize our data. So there are a couple of examples how we leverage this kind of the data. So we can take a data-driven approach when in terms of the feature roadmap, for example. So we can study production workload and the cloud across all the customers, and we are not able to see the data itself, of course, because this is the customer data, but we should be able to see the telemetry. So for example, here, so top target functions. So for partition pruning, as I mentioned earlier, so these are the predicates like count, how many usage for that specific kind of expression as a condition in the predicate table filter. Then we may want to like prioritize these heavy hitters to improve the pruning kind of the efficiency. So continuous monitoring is really the critical here. So on a daily basis, there are billions of the production queries. And also there are very long tail of the functions to improve, as you can see here. So we may want to first prioritize the topmost heavy hitters first. And data collected across the billion of the production queries runs in Snowflake each week and on a daily basis. And often, with the minimum effort, like if you want to target this simple predicate, probably it might be easier to implement a very well-scoped targeted solution for pruning, for example, instead of having very complex but more complete solution. We want to deliver the more impactful kind of the solution as early as possible without over-engineering. So that's the basic development philosophy of the data-driven development. And another example is the data-driven performance optimizations. So once we identify the certain area of improvement, so here are two examples. Common table expression improvement. So this is the compilation time. So we identify the compilation time inefficiency from the workload, and we implement this improvement, and after enabling this feature slowly, make it available for all customers using Snowflake, because we do the release, the weekly releases, it will be available to every customers very quickly. And then we can clearly see the impact of the certain kind of the performance optimization, as you can see here. So before enabling this specific improvement, this is the compilation time, how much time during the end-to-end query execution, how much percentage of compilation time was consuming. Now, after enabling this common table expression compilation time improvement, you can clearly see that there has been the performance improvement there. And also, second example is the scan improvement. So this is the credit usage from the customer. So they are, for the same amount of the scan jobs, the queries, customer have been using this much kind of the credit, kind of the money. But after enabling the improvement we made in the scan set, in scan performance, so now customers are paying way less money on the same workload. So this is why this is the performance optimization we are delivering for customers behind the scene seamlessly. So this is largely, I mean, thanks to our infrastructure, which we call the Snowtrail infrastructure. So data-driven release testing. So what it does is to sample the representative, the production query, and rerun the customer query on different version for really kind of true A/B testing. And to keep the cost low, we want to cover every feature while running the fewest queries as possible, and maximum coverage with a few thousand queries per release we want to target. So because we have the usage tracking kind of the metric, this is possible. So we can kind of collect some representative samples from the billions of the production queries. And we sample these representative queries with a greedy algorithm, very simple algorithms, like just kind of the random sampling for certain usage tracking. That way, we will be able to test the upcoming release at the same time. Like we should be able to test out all the features we are developing for the performance improvement. Then for optimizer improvement, it is not always 100% positive. Like sometimes, because optimizer is based on the estimate, improving the accuracy of the estimate doesn't necessarily mean that every query will get faster. So majority will get faster, but there will be the outliers. So by doing this Snowtrail testing, we should be able to easily identify and figure out what are those kind of the outliers, and if there are any like approaches we want to take to like outliers, and how we want to tackle those, and do we want to like roll out this improvement for certain set of customer, which, I mean, who don't have those outliers first, and then make some additional kind of the improvement on top, then move over to the next set of customers. So that kind of the data-driven kind of the rollout approach is also possible thanks to the Snowtrail infrastructure we have internally. So this is Snowflake Performance Index SPI. So this is what we publicly kind of make it available for customers. This is captured from the Snowflake website. So yeah, why Snowflake measure the SPI, Snowflake Performance Index? So Snowflake succeed when our customer get the benefit. I mean, the customer does succeed. Snowflake constantly innovates on the performance front with the goal of the reduce the customer cost over time, and regular performance improvement to the platform are kind of the proven kind of the track record of putting customer first. And Snowflake also intelligently optimized performance, no custom action required. And as you have seen earlier, previous slide, we have the way to like simulate and run the customer query without any side effect, and without the breaching the security, of course. And also, this is the representative example of the real-world query, so different from some arbitrary benchmark, synthetic benchmark like such as the TPC-DS. This is the real-life production workload. So real-life production workload just gets faster. So Snowflake uses real customer data to drive performance improvement and features, not synthetic benchmark. So this SPI shows improvement on actual customer workload. Yeah. So probably it's yeah, I think it's last slide or two. So Snowflake the AI as an AI data cloud. So we have the many challenges here. So data is fragmented and data is moving from one to another, and the data is scattered across various systems. So the OLTP system in the front end, data warehouse, data lake, and operational databases, as I mentioned earlier, and data movement, copying data for AI ML creates a latency and also costly, and the data governance is an issue there as well. And there are too many tools, like a data scientist often juggles many tools for different stage of the machine learning life cycle. So Snowflake's solution is to bring the compute to the data and unify the all data in one platform to be a one-stop shop for everything about the data, and eliminating the data silos and reduce the data movement and simplify the governance. So Snowflake as an AI data cloud is the single source of the truth for all data powering AI ML, and provides the necessary scale, performance, and governance for the entire AI ML lifecycle. And beyond traditional SQL capabilities, Snowflake is offering the improving the feature space as well, so scalable and easy to use SQL. So just a couple of examples is the kind of the relatively recently we introduced the higher order functions as a SQL native SQL flavor, and also the pipe operator. And also advanced analytics, especially around the time series data, is also kind of the important. So we recently introduced as of join. As of join is a mean of kind of the joining tables with time series data when corresponding timestamp columns contains values that do not exactly match. So for each row in the table, find the closest match value from the partner table. So that's the basics of the as of join compared to the traditional exact join kind of the mechanism. And also the beyond traditional SQL, the business semantic awareness is super important. So we recently went to the public preview of this semantic view. This is something I want to demo if possible as well. So native semantic view, this is to serve the context analyst semantic model. So we store the semantic model as a Snowflake, the first class citizen, like a relation of the object in a database schema, and it helps define the logical table structure that typically correspond to the business entities with dimension, metrics, and fact. And also benefit of serving this as the database object in the database schema is it serves as a first class citizen, and model will be validated, and data governance such as role-based access and row column-based access data governance data masking will be naturally kind of the automatically available to use. And semantic aware performance optimization is also possible. For example, we can eliminate join when there's unnecessary if there's a unnecessary join under the hood. So all the traditional kind of the query optimization mechanism we can apply for this semantic view.
Youngshik, maybe we can stop here and take some questions, and then come back to demo, because the
Okay.
time there's some people are leaving because of time limit. Any questions?
All right, maybe
Thank you for showing the picture 20 years ago. This is exactly 20 years.
10 years ago.
When I started, when the SAP called me, called me to come to Heidelberg and at 4 a.m. In the morning. So, the discussion with the SAP merger started around this time anyway. So there's questions. Lucas is also, you are in Germany and you're probably in the middle of the night. Maybe I'll give you the first chance.
All right, thank you. So first off, kind regards from Johannes Osterhoff. He's also with SAP right now in the headquarters, so maybe you remember him, Yongshik. So kind regards from him. And I also have another question. So whenever you try to optimize within your career optimizer for certain customer scenarios, like I think it's inevitable that you will have some kind of performance regressions, right? So how do you handle those? Do you put like an exception there when customer X runs workload Y? Do you sort of enable the old path from the career optimizer to enable the old given performance? Or so how do you handle that? Because at SAP, people see a lot of those regressions, and so they decide to not run Hex and instead take the old attribute engine, right?
Yeah, exactly. Yeah. So when I shared the Snowflake, Snowflake is the first company doing the weekly releases. This speaks for itself, right? This means a lot. So we internally
we had the daily release when Yongshik, we had the daily release when we started SAP HANA.
Yeah, but with the large set of the mission critical kind of the enterprise customers, weekly releases is like it doesn't come free, right? And one of the project I started here as Snowflake is the so-called plan stability. So we want to provide a safety net to cover the customer from hitting the regression when we roll out any kind of the features. But even without any features, like underlying data changes, we'll end up having the performance fluctuation because plan changes depending on the data statics underneath. Even though we don't touch anything, there will be the performance fluctuation in the query. So we want to capture the previous execution for recurring queries, and we keep track of those history and certain join order, for example. And then we can capture that, and we can force the certain join order when we detect a certain regression. For example, like it runs more than like twice of the previous execution, we will cancel the query and we will pin the previous plan. This is just to provide a safety net, and we are still working on how to make it better and better. And also that there is a regression mitigation mechanism so that we parameter guard each and every changes. So then you can flip the parameter to enable certain feature or performance optimization internally. This is the internal parameter we can control, but not for customers. So we build the automatic system behind the scenes so that we can automatically detect such a regression. If it comes from our newly introduced parameters, we can turn off those parameters simply. Or if it is coming from the data changes from customer end, we can force the certain shape of the plan.
Okay, so I would also have a related question related to that. So do you have also internal discussions on, whether to forego any kind of regression concerns and just accept the fact that maybe you want to keep the code base simple instead of introducing additional complexity, because additional complexity is like a major factor to development cost, right? And if you just have a customer who runs the workload, maybe not too often, but like the induced cost, yeah.
Yeah. So we don't know whether this new regression will end up having the kind of the very serious issue from customer, right? We don't know whether they are okay with those regression or they are very unhappy with those new regressions, right? So yeah, you're right. I mean, sometimes we have to like go with it, like with a certain kind of the regression, because the plan stability and regression mitigation is not 100% perfect. So there will be the outliers and regression still, and then we want to respond to those kind of the regression really quickly, but that will be like customer by customer. Like if they are like large customers and concerned about the day-to-day operation of their workload, and those workload will be taken care of like way more importantly than other kind of the normal workload. And in average and in aggregate, performance will be improved. But when you look at the like outliers, each and every outliers, I don't think we can tackle everything there.
Yeah. Okay. Sounds great.
But we have the data, and we have to do some experiment there as well. How aggressive do we want to push things forward? So that's the question we always have. Like, yeah.
I mean, like the customer-centric approach and also the access to data is something which I would really appreciate if I would have the same. I speak out of experience there, so it's quite remarkable that you are allowed to and that you are in fact encouraged to do that. So I think that's very great. So yeah, thank you.
Yeah, thank you.
So now Vincent, Professor Lee.
Hello. So I think you mentioned the unstructured data and the large language model are two innovation area Snowflake is looking into. So you mentioned semi-structured, you mentioned unstructured data, but you didn't mention large language model. Are you able, have liberty to say something about this? Because large language model is very different from all other data that database area has been working on.
Yeah, so reason why I didn't
By the way, the CEO of the Snowflake come from AI area, so not the database. So they acquired a company and then they made the CEO of that company the CEO of Snowflake.
So we internally have very close collaboration with this AI team. I mean, as a kind of the serving layer. So my team is more of the core engine team, right? And then there's many performance issues they want us to help out. But they are more or less like a technical, traditional kind of the database problems rather than the new issues, to be honest. And like introducing the like new data type like such as vector, for example, and array data type and structured data type, and also AI joins. They want to introduce the native AI join and AI filter, which requires some enforcer mechanism to sort and filter out the data before calling the LLM logic for AI join, for example, because it is too costly. So those kind of the performance optimization, we are like collaborating, very closely collaborating each other. But yeah, that is something I honestly have the clear, like a big picture of it, like, because this is not my expertise area, to be honest. But yeah, we are very closely collaborating each other to improve
We
the
are
performance
experiencing
from.
the network problem. Obviously, I was disconnected.
Oh, okay.
All right, thank you.
Okay, Lucas.
I think Professor Cha's internet connection got lost. Anyway, so maybe if you don't mind, I would like to ask about like Aurora maybe on AWS. So it seems like that Amazon is taking a federated approach with regards to let's say HTAP workloads. So I mean, like I saw some slides by some people who mentioned that Redshift is a HTAP database, but it seems that out of the box, that this is actually not the case, right? Like you got Aurora for OLTP and you got Redshift for OLAP. So is there like anything that like co-joins those two platforms to enable like mixed workloads, and do they have any sort of MVCC going on, or do you know anything
Yeah,
about
that
this?
has been the case when I was there, but when I was there were already some of the discussion happening between Aurora and Redshift, so that kind of the zero ETL kind of the idea. Like for example, we can leverage, from Aurora, we can leverage the Redshift, the analytical engine on top of the Aurora data layout without copying it to the Redshift data layout and vice versa. So because of the decoupled storage and compute, that should be possible. So yeah, I think they worked on towards that, and I don't know the latest state of the project, but to my understanding, they did something around it and announced it.
Okay, thank you.
I think we are muted.
So maybe it's good time for a short demo. People who want to stay on can stay, and for just a quick demo. Yeah.
Yeah, I just wanted to show the very simple demo here, like
Mhm.
semantic view we have. So let me see if I can successfully showcase the demo here. Like this is the Snowflake notebook. And you can see like with the semantic view, you can create a semantic view through SQL. And this is the TPCH kind of the like example, like the relationship between the multiple entity and tables. And you can define the this kind of the relationship with the semantic view SQL. But in this case, I want to kind of the demo with a more complicated TPCDS scenario here. So there is all the different tables from TPCTS. Oh, sorry. Yeah, as you can see here, we have all the TPCTS table, and then we can create the semantic view around the TPCTS table, like a customer and store sales, and there is a relationship between those kind of the tables, and fact is defined and dimension is defined, and also the metrics is defined, like a total cost, sales price, and quantity. So you can create this semantic view here between the multiple tables.
So how is it different from the ordinary view? What do you mean by, what do you add by semantic?
So this is kind of the preview feature, but we're gonna add more and more semantics from BI layer, so that this is more of the hierarchical description of the BI logic. So for example, like, oh, let me see if I did something wrong. Yeah, I first need to use the database, and then I can create a semantic view around it, and then I can describe semantic view. And then as you can see here, so all the object name and the dimension and fact and relationship between those tables, and metric is available. And there's also the relationship kind of the description will be available, like end-to-end relationship, end-to-one relationship, and to exactly one relationship. Those kind of the things will be added here. And then you can also query over this semantic view as well. Here, the simple example is the like what are the top 10 brands in the books category in the state of Texas for year 2003. Like year 2003, books category Texas and top 10. So you can see that is Maxi number 2 is the top most one in the Texas. And if you go into the AI, like Cortex Analyst, you can also select this semantic view, and you can see all the view I just created, like logical tables. So this customer table, date, demo, store sales, and you can see the metric like cost, price, and quantity, and all these things you can see here. And then what you can do is the like plain text. Here, what I can do here is like,
So it allows natural language queries.
yes, so
So that's the point.
are the top 10 brands in the same question, books category in the state of Texas. Oh, let me see.
So semantic views are essentially to support conversational natural language queries.
Yes. like,
Does it understand the context like the OpenAI ChatGPT?
yeah, basically. So this semantic model is powering the Cortex Analytics LLM model at the top, and then you can see you can ask the plain text query, and this Cortex Analyst will understand a semantic model and generate it, like for example query like this, and then this will be the answer, which is exactly the same for the one I just executed before through query. So
that's because of you focus on this the star schema.
Yeah.
So you understand the star schema semantics, and
Yes.
it enables to translate natural language queries to the SQL, more correctly than
Yeah, this was the simple demo I wanted to showcase here.
Okay, good. Yeah, that's good. Yeah. Any questions on this among the audience? So what kind of the LLMs you use? Is it open source?
Yes, open source, all different flavors the Snowflake provide.
So the question is, if I choose some open source, whether it's Llama or if I choose some closed LLM like OpenAI, then can I still plug in and then use it?
Yes.
Okay, so that's good. Then
Snowflake contain a service so that you can bring in your own kind of the model and functions.
Okay. But on the other hand, it generates some metadata for the LLMs. Snowflake generates some metadata for LLMs.
Yeah.
For fine tuning, whatever. Yeah. Lucas, do you still have a question? You raise hand.
Sorry for asking so many questions. So first off, so do you provide, aside from a flattened view for the descriptive model, do you provide any additional data in the preamble before you actually send the query to the LLM? Like for instance, when you have like a flattened view of this semantic data description, do you, for instance, put like yeah, we want the output to be shaped like this and that? We typically or we identified that this is a star schema. So is there something additional working under the hood? Because if you deploy just any LLM without any fine tuning, I can imagine it's quite hard to get a deterministic output, right? Well, I mean, like deterministic output is not given for LLMs anyway, but you know what I mean. So
Yeah. No, I mean so what I showed is everything I did, like just create a new semantic view and then asking questions through the plain text language, and it was able to answer my question. I don't know what is the magic behind, to be honest, but it was able to answer that. But if I tweak a little bit, for example, it was like for now it will be improved over time. But as you have seen, my question was the state of the Texas as a TX, and it used it as a Texas the state code. But if I use a Texas TEXAS, then it will take that as a condition, and eventually the empty result will be shown. So that might be something they need to improve in the model, so that this Texas will be mapped to the TX instead of Texas itself. So those little bit of those kind of the things need to be improved further, but it is still kind of the preview stage, so it will improve over time. The team is working on really hard to improve the accuracy of this model. But what I have shown today is everything. Like there's no additional kind of the processing under the hood.
So the Vishal has his company. His company actually developed conversational, the analytical, the solutions, based on LLM, and then it actually deals with the ERP database. So you ask it, some questions like, what is the revenue of certain product for certain quarter, or what is the fast growing the product, fast growing revenue items, or whatever, so you might want to take a look at what's the difference, and what additional semantics do we need to deal with this kind of a conversational interface.
Yeah, that is something I need to learn as well. Like I'm not the expert in the AI space, so we are
It's
collaborating.
easy to, you just need just some spare time. You can even ask Lucas.
Yeah.
Okay. Well, thank you. Maybe I call you in a minute, if you have a time. Yeah.
Yeah.
Okay.
Okay.
Thank
Thank you
you.
very much.
Yeah.